All right, everybody, welcome to yet another OpenShift Commons briefing. Today is, as we are wont to do on Mondays, is an upstream project AMA Ask Me Anything session with NSM, Network Service Mesh, with Ed Warnicke and Frederick Kautz, who are going to walk us through, give an intro to this topic, tell us a little bit about the roadmap, what's going on in that community, and then we'll have time at the end for Q&A. So as we're going through this, it's live streamed wherever you are, Facebook, Twitch, YouTube Live, or in Blue Jeans with us here. Type your questions into the chat and we will relay them to our guest speakers today. And so without any further ado, Ed and Fred, take it away, introduce yourselves, and tell us all about this wonderful community.
Sure. So my name is Ed Warnicke. I'm one of the founding committers on the Network Service Mesh project. It's a CNCF Sandbox project. And just sort of by way of general housekeeping, I say this all the time, and Frederick is quite used to it. Please feel free to ask questions as we go, because if there's a question that occurs to you while we're going through just sort of the brief introductory slides, then it'll probably occur to other people. And since this is an AMA, the slides are really primarily here to foster conversation and to spur questioning. That's really sort of the important part of the exercise in my view.
Yep. Hello, and I'm Frederick. I'm also one of the people working on Network Service Mesh. Ed and I started it, and it's grown quite a bit. So we're here to talk about what we are doing and some of the directions that we're heading towards. Again, same thing. Feel free to ask questions along the way. We're more than happy to help out. And so with that, let's jump straight into this. So from a housekeeping perspective, we have networkservicemesh.io as our main website. We will post the link to these slides on. We'll make sure that they get posted in the OpenShift Commons place and wherever those slides tend to be stored, so people can gain access to these. And we also have a longer form of these slides in the form of a webinar. So in terms of NSM Vision, we're gonna go over three particular areas. So one of them are some of the problems we're trying to solve, and this is not a exhaustive list of all the problems. This is just one set of problems that we think will be useful to the audience that is here. We have a list of things that we believe are not really solutions that we want to drive towards, and that describe some of the problems that we see that we see are currently happening, and then we discuss when we bring NSM into the table about how we can simplify some of these solutions and get them to a place where they can become tenable. And so the first concept is, if you think of Kubernetes as a runtime domain. It's a domain that you run your pods in, your compute in. And with every Kubernetes runtime domain, there is a connectivity domain associated to it. This connectivity domain, from the perspective of Kubernetes, is pure layer 3. You will not see MAC addresses in any of the Kubernetes tooling or any of the northbound APIs that they expose. You will see service discovery and routing, which is typically handled through DNS, and you will see isolation through the form of Kubernetes network policies. You're thinking of like ingress policies, egress policies. You'll see services and where they land you. Optionally, you'll often see a layer 7 service mesh, an application service mesh, which Istio, Linkerd, and similar are great examples. And the connectivity domain within Kubernetes, even though there's a lot of flexibility in the definition, the most common trend that you see is intra-cluster. In other words, pod to pod, app to app, or you could have something that handles your ingress to your pod, and so on. That doesn't mean that there is no external connectivity, but for the purposes of the connectivity domain itself, that it tends to focus on what's within the cluster.
Yeah. And so these two things are sort of important to think about. as we move forward through the world. So one of the hallmarks of cloud native is that more than anything, it's a rethinking of problems. As we progressively virtualize the world, one of the things that we've realized is that we've unnecessarily brought along physical constraints that were true about the physical devices, servers, networks that we all started with in the late 90s. And that often these end up being simple boat anchors. They actually don't serve us. They actually hinder our ability to solve our problems. And so the history of cloud native is the history of stopping to rethink these things. And one of these physical artifacts has always been that your runtime domain, in other words, where your workload is running, is connected to precisely one connectivity domain. Originally, back in the 90s, it was your physical networking, your data center. And that even though that there may be a bunch of different nerd knobs that could be turned, it was precisely one connectivity domain that had precisely one set of things on offer that was run by precisely one administrative entity. And we carried that thinking forward into Cloud 1.0 with VMs. And then while we've gotten much, much better about how we think about that networking, where Kubernetes has thought about it in more general terms of services, service discovery and routing and isolation rather than IP addresses, we still think about the fact that where I run my workload determines precisely who it can talk to and the rules they can use to talk to each other. And that's the thing that we need to actually start thinking about separately instead of as a single glom.
So when we start to think about these particular domains, and so when we start to spin up multiple clusters, so because we have this style of thinking where every container, every Kubernetes, or to say your runtime domain is directly attached and has the exact same shape as your networking domain within the cluster. When we spin up multiple clusters, we get something that looks like this diagram on the right. Like each of these is effectively an island, and there's something in the middle that may or may not allow communication. And what form of communication does it allow? It's not defined. And so what ends up happening is when we start to connect, when we start to talk about connecting the workloads into other workloads, we tend to think of it as a community about connecting the networking domain with each other. Like let's say we'll start taking a look at intercluster workload isolation. So we'll have these 4 clusters, and how do we set up these networks so that they're capable of communicating each other? So a very common technique that you see is that and we saw this prevalently in earlier Kubernetes time, and we see this waning a little bit more as time goes on because of the complexity behind it, is to establish a subnet, a different subnet for each of these clusters, and then to wire them all up so that they can be routable, so that when you decide to connect from one pod in one system to a pod in another cluster, then you're capable of performing that form of communication. But one of the problems that we run into, though, is that recall that the policies are also intra-cluster, not intra-cluster. And so what ends up happening is you end up with pods that should not have been able to communicate with being able to communicate with each other. And
this, by the way, is a good example of being constrained by the physical thinking of the past. Because if I had different data centers that needed to talk to each other, I would set up data center to data center networking. And so the intra-cluster thing is the first natural thing that comes to mind for people. So doing cluster to cluster networking, because that's how we handle the physical data centers. But as Frederick sort of pointed out, it has a number of problems, not the least of which is that I'm going to make a very bold statement. Nobody actually wants 2 clusters to talk to each other. They want workloads that happen to be in 2 clusters to be able to talk to each other. And not all the workloads in both clusters, but some of them in each. And that's the fundamental thing that we start realizing.
And so, in terms of the complexity of the system as well, so eventually when you start to hook up multiple of these systems, like when you have 4 systems, you have 1, 2, 3, 4, 5, 6 connections. When you add in a 5th system, a 6th system, a 7th system, a full mesh, the number of connections, the combinatorics on that grows quite significantly. And if I recall, the number I believe was the number of nodes you have times the number of nodes you have minus 1, then divide all that by 2, and that's the total number of links that you potentially can have between these type of systems. And so if you're only setting up 2 or 3 systems, it's not a big deal. If you're setting up 30 of these things, 40 of these things, and they have to communicate each other across multiple clouds, multiple regions, then it becomes a huge problem. And
or God help you if you have 50 of them, which a goodly sized enterprise, you may eventually get to that point.
Absolutely, and then you also have to work about how do you actually configure these things? Like, who's going to set up the links? How are you going to organize this information? There still has to be rules between them on how to prevent them from communicating with each other in ways you don't want them to. So then the firewall rules that they get attached to that can become incredibly complex. And people are bringing in things like layer 7 service meshes to try to deal with some of these things, but you still end up with the problem of application gateways that you have to go and configure each one and set them up. You still have the problem of having to synchronize all of the state between every system that's there, and you still have the problem of identity between them. How do you work out the identity of the things that you're communicating with, which is beyond the scope of what we're going to talk in this scenario, but there's a lot of complexity that comes in that's hidden, that comes beyond just we just want to hook these things up when with a networking in a networking layer. And of course, service discovery and routing between them. Like, how do you even set up the discovery, and how do you route between pods or between the systems? So what we effectively are getting when we try to take this approach is we're seeing basically the network domain trying to be spread across all systems in an equal way. And so this is where, when you start talking about federated multiple clusters, one of the problems that you have with this is saying, oh, let's bring in a single SDN and we'll have it own everything that's in there, and the SDN will deal with everything that's there. But you still have you've automated some of the combinatorics work that goes on, but you still have an explosion in state, and eventually that SDN is eventually going to hit its limits, and you still have problems with how do you define and determine the services and network policies, and still manage to scale that and simultaneously keep your latency requirements on updates. So
yeah, one very simple way to see where the federation on solution will start to break down is if you look at the scaling of Kubernetes itself, right? So Kubernetes effectively keeps a small set of very simple, mostly read, seldom written to objects in the API server. Things, like your CRDs, your pod specs, your service specs, etc. But even there, Kubernetes technically, I think last time I checked, the stated limit of the size of a cluster was 5,000 nodes. And long before you get to that point, things start to get creaky. And it's primarily because of the scope and the change velocity of the state in your API servers. And that's about as good as it's ever going to get, because those API servers tend to be located in a single cluster where everything is at low latency to each other. When you start playing the federation game, effectively, the simple way to think about it is you're taking the same sort of game that you played in a single cluster of centralizing some state, and you're blowing the combinatorics up beyond the scale at which your clusters are normally breaking down. And you're making the problem worse by introducing greater latency, greater partition potential, et cetera, because you've got clusters potentially running across the WAN from each other. And so it's not at all surprising that trying to federate in this way faces very significant challenges. And it's because it's taking something that was extraordinarily well designed at the scale of, at cluster scale, and extraordinarily well designed for an environment of low latency within a single cluster. And it's trying to project to something at much larger scales than it was ever designed for, with much, much worse latency impacts than it was ever designed for. And so effectively, you very rapidly run into problems with this, particularly as you scale up the number of clusters. And it's really just taking a tool that has been brilliant when utilized in the scale and manner in which it was designed, and pushing it beyond the same limits with which you would attempt to use it.
So, yeah, and this complexity gets even worse. Like once we start to add in other types of compute domains, such as virtual machines, which run on systems like Neutron, or we bring in on-premise servers that may not have Kubernetes installed on them. They may be running top-of-rack switches or other types of hardware that provides networking that you may need to integrate with. But everything looks like a Kubernetes federated cluster. Then trying to integrate these things in a holistic way becomes a serious challenge with this federation approach as well. And so
it's very much a semantics problem. It turns out every connectivity domain has a certain semantics to it. It's how it thinks about how workloads communicate with each other. And the way that Kubernetes thinks about workload communication with, basic L3 communication at pure L3 with network policies, with services, et cetera. That's one way of thinking about intercluster, about connectivity. The way you traditionally would think about things in terms of, in terms of L2 subnets, and that sort of stuff, and security groups and everything else. In a virtual network with VMs is a different way. And then every data center has an entirely bespoke set of semantics about the various nerd knobs and how it's basically built out, how it thinks about communication between workloads. And these are sets of semantics that literally aren't easy to reconcile with each other. In fact, often they're impossible to reconcile with each other. And the real problem is, again, you've welded your workload to precisely one semantics of communication. And that's where it all starts breaking down.
So in this scenario, when it's like, so this covers like the L2 and L3 side of of a common federation pattern that we see. We also see at the very top saying, well, let's go hook up everything at the L7 layer. We'll get something like Istio, or we'll get something like Linkerd, Kuma, and so on, and we'll spread that across everything. So instead of working at the L3 layer, like we were discussing before, we'll do this at the L7 layer. The first problem with this is that this only works for layer 7 things, and there's are significant number of problems which require a layer 3 base solution. This is especially true when you start looking at some of the work that is being done in the telecom space, who are also trying to deploy on top of Kubernetes. That for them, they're defining and bringing the L2 and L3 data planes, and so saying, oh, you should run on top of L7 certainly doesn't work. But even in the case of an enterprise network where you're not trying to be a telecom, you still have significant problems with driving everything through L7. And you still have problems with the full mesh combinatorics, like what are you going to expose, how are you going to manage the state, how are you going to push them around, and you still have the same manual cluster and link setups that between every different types of cloud provider that exist, and including the complex firewall rules that you still have to set up between them. And so the biggest problem as well that this makes, tying it to the L7 and not L3, is that it's making the assumption that every single one of these systems already has an underlay set up. And what we mean by an underlay is you can think of these types of connections as being an overlay. an overlay network. It's a network that sits on top of another network. Even if it's even if it's a type of system that they're doing TLS connections and tunneling through that, you can still see that as an overlay. So if I asked you hey, hook up Azure and AWS, then they're not immediately going to be able to start talking with each other until you've done some initial setup work in order to get them to start to communicate with each other. So you still have that underlying L2, L3 problem, even when you bring an L7 mesh on top of it. Same goes with on-prem. You end up having to set up your VPNs or your peering with AWS, Google, and Azure, or you hook onto Google and so on. So it's the same problem, and it can help you with managing some of the discovery issues that appear at the top, but you still have that core problem that sits underneath. And so our realization is that in welding the connectivity domain to your runtime domain, when you want to have multiple clusters in this scenario, is a mistake, and that we want there to be an independence between the connectivity domain and the runtime domain. So what do we mean by connectivity domain independence is that we have to look at what is it that we really care about. Do we really care that the Kubernetes networking itself is capable to talk to the other networks, or do we care about the capability of a pod to communicate with another pod, or a workload to communicate with another workload? Like whether it ends up how this gets rendered. It could be through Kubernetes networking, whether it gets ran through something else. The developer doesn't really care. The operator cares, but they don't really care about the detail as to whether it's all being forced through the Kubernetes networking through the connectivity domain itself. And so the solution that we're aiming for and that we've developed towards this is to leave intercluster networking alone. The intracluster networking alone, rather. So the intracluster networking itself is fantastically well done as long as you're staying within a single Kubernetes cluster. It's a very well solved problem. So we don't want to break that. But at the same time, we want to be able to enable communication between clusters, and while at the same time being harmless to existing Kubernetes networking.
This is actually, if we could back up real quick, this is a really crucial point that's sometimes underappreciated. Historically, the way that you've tried to solve having additional requirements in networking has been you just keep pouring more and more crap into the same networking domain. And it gets more and more complicated and more fragile and harder to evolve and harder to change, and more prone to having issues as you keep labeling more stuff in. And one of the really deeply beautiful things about Kubernetes networking is its simplicity. It's very, very simple. And that makes it extremely robust, very easy to reason about, very easy to use. And so it seemed to us that trying to go and persuade Kubernetes networking to do sort of a potentially infinite number of increasingly complex things probably was going to make everyone else miserable and wasn't really going to produce a good solution. And so it works, leave it alone, make sure you do nothing that can break it.
So the next step after that is that we want to then create a connectivity domain that is not welded to any given cluster, but instead is one where we can hook up specific workloads to a specific connectivity domain. So perhaps we have a database replication. Let's say that you have use Vitesse as an example. Maybe you have a Vitesse on each of these pods, and you want to perform some form of replication between them. Then what we can do is we can establish a connectivity domain that is specific to them, that allows these systems to connect through that path only for those particular purposes for that type of communication. And so what this does is and then you might spin up another one, which is an Istio-based one, and you want these systems to communicate with Istio and have Istio-controlled policy and to be able to work with that. But it being set up so that Istio itself is in its own connectivity domain, and that allows you to bring in your connectivity, your security, your observability. It all allows you to avoid commingling your connectivity domains and such, so that like your replication data is not traversing over Istio or vice versa, which means that not only does this get certain security properties that they get enabled, but also you could give it a different performance treatment. You can give it different latency or throughput requirements, have it go through different data paths that perhaps your Istio systems are not going through in order to further reduce that latency. So by separating them out, it gives us a lot of control.
It also has the nice benefit that it is possible to have networking semantics that make sense for the particular set of workloads that are communicating over a network service or a connectivity domain. So for database replication, maybe all you need is something that's virtual layer 3. Everybody can talk to everybody over IP, together with basic admission controls, so only your databases that should be replicating are allowed to connect to it. And you can make that scope of semantics as precisely matching needs of your workloads as you need, and the scope of admission as narrow as makes sense for the problem you're trying to solve. An enormous amount of the complexity that we produce in networks around security has to do with the fact that you've got many things with disparate needs, disparate security characteristics, et cetera, participating in a single connectivity domain. And then you have to bring very complicated policies to manage that. If you could instead just say, look, the only things here are stuff doing database replication. And the only things that we have to provide to them are network, features of a network service and semantics that help with database replication. That makes the world enormously simpler to work with. But it also means that you can simply say, hey, we're going to let the guys who are managing the databases twist what very small number of nerd knobs there are for the database replication network service, because it's their workload, and if they can manage that themselves, and if they do something, it's not going to screw up everybody else's workload. You can give them administrative independence. You don't have to have one giant networking organization taking tickets to try and resolve the needs of thousands of applications.
So, and then when we start to look at bringing in other types of virtual networking domains, such as your VMs or your on-premise servers, then by separating these out, it also reduces the chances. Like, you don't have to deconflict the entire world. Like, you're not starting with global state. What you're starting with is local state, such as database replication. What things do I not need? What things should I not conflict with within the clusters I'm working with, in order to get something working with, rather than looking at this from a global side. And simultaneously, it also means that you can do the right thing for things such as virtual networking and on-premise servers, without having to worry that you're going to conflict with, or that you're going to break the Kubernetes networking path. So bringing in,
essentially by associating the semantics of your connectivity domain to the connectivity domain itself, rather than to the runtime domain, then any workload, wherever it's running, can participate in a clean way, rather than having to resolve all these different semantics that are welded connectivity domain by connectivity domain.
So we have a slight divergence as well, because all of this stuff we're talking about, there's also a security component on this that we're heading towards. And so in terms of the model that we're heading towards is one of this called zero trust. And so the basic concept behind it is this should look very similar to the first non-solution that we described. You have trusted network connected to another trusted network. In this scenario, it could be Kubernetes with pods in them, which are workloads, and then you hook up some form of a tunnel or VPN between them. And the way you defend them is you stick firewall rules and access control list and so on the perimeter, which then defines how they can communicate with each other. And Kubernetes takes this a bit further. It does have some the ingress and egress rules, which help, but it still follows this model to a wide degree. A zero trust environment is what you're doing is you're saying we're going to attest the identity of a workload. So instead of having this be this VPN be the identity, the thing that we're connecting with at the VPN endpoints themselves, we're saying that the workloads themselves actually have identities and that we can work out who they are. And what we do is we assign a cryptographic identity, typically in the form of an X509 certificate, to these workloads so that when they connect to another workload, they can do mutual TLS between them, which means that not only does the client validate the server and the server's identity like you would in a website, but the server can also validate the client's identity and work out who that entity is. And this has two nice effects. Number one is you know exactly who you're communicating with, regardless of whether you're the client or the server, and regardless on what network they're on. And simultaneously, it also means that you can apply your policy not at the IP level. Instead of saying, you know, these IPs are allowed to talk to these IPs. Instead, you can say these workloads with these cryptographic identities, the API gateways might have a specific identity in order to connect to a backend API, like a payment gateway or so on. You can give them identities that you can then reason about. So when you're scaling Kubernetes and you decide to scale it out horizontally, or you reduce the size of your scale, even if you have them in separate clusters and they're communicating with each other, you can still establish this secure connection that has a strong cryptographic tie to it. And so if an attacker enters your untrusted network, then they don't immediately have an identity. And so just entering the network itself does not give it the capability to perform actions on your network. And so this doesn't negate the need for the workloads themselves to have to follow best practices in terms of security. Because of course, if someone breaks into the actual workload, then whatever that workload's allowed to do is within that context, then the attacker can do. But it severely limits the type of thing that an attacker can do where they break into the workload and they decide, oh, I'm going to do a scan for open databases. It's like if they don't have a policy that allows those databases to connect, then they're not gaining access to that database because they won't be able to connect to that database. And so, in short, the identity part looks similar to this. You have a CA at the top that attests and gives identities to your workloads. Let's say like an application service or a database service, and then you can perform that policy on top of it once they receive these identities. And so in the case of network service mesh, when we start talking about these things, like suppose that the service you want to connect to, similar to maybe application wants to connect to a database, you have an app that wants to connect to a secure corporate intranet. It is a network service. And so as the app developer, you don't want to have to worry about what subnet am I connected to, how do I set up the interface, how do I set up the routes, how do I set up, what do I have to configure in that path? You just want to be able to ask for that service and receive it. The operator, however, may have a requirement on what does it mean to connect to, in this case, secure corporate intranet. So the operator might say, well, in order to connect to this, by policy, we want you to connect to a firewall, an intrusion detection system, a certain VPA gateway, which might connect to a certain VPN concentrator. So you have this chain that gets created, and you want to enforce this particular path. And so the first thing that you see happen in these type of scenarios is you separate out the control plane from the data plane, and this is a very common theme in networks. You even see this in hardware switches, like the control plane and data plane will be separated from each other, and that way you can control it and update your control plane and give an easy model that you can then manipulate your data plane. So we follow the same pattern where in Kubernetes we're able to, or your connectivity domain, you establish this control plane that says there's something that's going to work and interact with the pod. There's something that's going to interact with a firewall. There's something that will interact with the intrusion detection system and the VPN, and they are able to communicate with each other. And each of these will then configure or manipulate the underlying technology that exists under it, so that when we connect, we can say, let's connect at the control plane layer first and ensure we can establish a full connection there. And once we've established all of that information, and then we can in line while we're establishing that connectivity, establish all of the all the rules and configurations necessary to actually make that thing a reality. So what this means is that every major item in your workload gets an identity. So the pod gets an X509 certificate, firewall, intrusion detection, and VPN, and the VPN itself gets an identity. And these identities are managed by these control endpoints. They don't tend to be, even though they can be pushed down, they don't have to be, the devices underneath don't need to be aware of the identity, as long as the endpoint itself is aware of that identity. And so this means that when the pod is told connect to this firewall in order to continue your communication, it knows exactly who it's connecting to, that it's connecting to the right one, that provides the right type of firewall with the right policies that are in line with policy of the operator, that allows it to proceed to the next step, which is the intrusion detection system and so on. And so in essence, we want something that looks like this. The app goes to the VPN gateway following that chain that we showed before, connects to the internet, and then connects to the VPN concentrator and API. And this allows us to build out that trust. Because we're using X509 certificates at this area, we can establish trust where even if you have two organizations that are communicating with each other and that are following the same pattern and are controlling their own set of identities, as long as we can establish some form of trust between the top level CAs, then we can identify, like, am I connecting to the right VPN concentrator? And the VPN concentrator can ask, am I receiving a connection from the right VPN gateway? All driven through that top level X509 set of certificates that were released with those specific identities. And also with the policy, usually using something like Open Policy Agent, although you can use others as well, defining what type of communication is allowed between those systems. So that was a foray into zero trust. These are all things that we've implemented within NSM that allows you to provide that, decouple your connectivity domain, simultaneously allows you to connect things together in a heterogeneous environment, and simultaneously do so with this zero trust identity and policy that allows you to control who can talk to what in a declarative manner without having to dive down into the low level specifics, like what IP address do you have, and having to perform access control lists that are based on the actual firewall rules themselves. So we still have, I think, 15 minutes. So Ed and I are here to take questions that anyone may have. And thank you all for your time.
All right. Well, thank you.
One other quick thing here. Again, we would love to see folks turn out for the NSMCon August 17th. It's a virtual event. The information is here, so feel free to please go register. That's literally a week from today. We've got a really good lineup of speakers talking about all kinds of network service mesh related topics from all across the industry. So should be a really good time.
And why don't you, Frederick, if you don't mind, pop over to that link just so we can see that lineup while we're chatting here a little bit.
Sure. So we don't have the names of the companies in there until you drop down, but we have people from Cisco, Charter, Volk, which works with CNCF. We have people from Ericsson, more Cisco. So we have VMware is giving a talk. We have one that we have not announced yet that is going to have Anthem involved as well. And so we have quite and Bell Canada. So we have quite a diverse lineup of topics on this.
And there's a lot of those are like Anthem and Bell and others are big OpenShift users too. So it's interesting. One of the questions I have, and thank you for the introduction because it cleared up a lot of things for me in terms of different service meshes and how level 7 and level 3 all work. It was great. It seems like we have dashboards for a lot of these things, and like, how do you manage all of this? Is no single pane of glass for all of my networking service mesh stuff, and how is that all coming together for people?
Yeah, so part of it really is, and this is what gets to be super interesting. When you sort of look at building a system like this and you're talking about single panes of glass, the question always is single panes of glass across which domain, and who is actually the administrator that's looking at that single pane of glass?
Mm-hmm.
And one of the challenges that you actually run into when you start actually growing up is that you discover that the world is much more complicated than a single administrative domain that gets subdivided. And this is something, I'm a deep network guy, right? And so this is something I'm very familiar with because the internet is not a single administrative domain that you subdivide. The internet is a bunch of peers. And so it's a different set of problems. And so the real question is, how do you give people visibility into the parts that they should have visibility into? And in network service mesh, what we have is some very, very simple, straightforward gRPC APIs that will allow you to monitor what's going on the pieces of the system that are actually germane to you. So for example, if you were someone who built the dashboard, so we don't actually, we had people in the community attach dashboards to this. For example, I forgot the name of it. A couple of topology dashboards have been connected to this API, but we don't provide a single one true dashboard for network service mesh because you're actually going to want to integrate it in with the rest of whatever your system is. And from that, you can see things like if I have an OpenShift cluster and I've got a bunch of workloads and they're connected to a bunch of network services, some of which may actually be coming from outside. In fact, most of which are going to be coming from outside my OpenShift cluster in some way. Some of which may be coming from outside my immediate company. Because, for example, maybe I'm a parts supplier for an automaker and I'm participating in a network service that's being provided by the automaker I'm supplying to connect to them and their suppliers. That's not something I am ever going to have control over, but I have enough visibility that I can see, okay, this is sort of like what's going on within my domain of control. My workloads that are attaching to it have these kinds of metrics. So I can see the problems related to my workloads participation in that network service, even though it's being provided by someone else. And so that's an interesting piece to get right around the visibility. But because everybody has their own dashboards that they want to use, the really productive thing to do in that space is to make it extraordinarily simple to get the kinds of information that you need and in order to function and do these things. And that's been a lot of what our focus has been.
Yeah, and to add to that as well, when you start looking at how do you control these type of systems, the network service mesh was designed specifically to allow multiple companies or multiple organizations to also be able to establish these type of chains. And so one example, I'll use a medical example since I do stuff within the healthcare space, is in the near future, we're going to have 5G systems deployed out, and we're going to have these edge data centers that exist. So we're going to see topologies where you might have a tablet or a piece of equipment, like a medical device, that connects not through Wi-Fi anymore, but connects through 5G to the hospital's data center, not to the edge data center directly, but to the hospital's own data center. And then that data center may have applications that run on it, but it may then connect to an edge data center, which then brings in like firewall as a service, intrusion detection as a service that are provided by third-party companies, or data loss prevention as a service. And then once you start to, and then that then connects through its own backplane to maybe AWS or GCP or some other type of system that to your VPC that you then control. So within this path, you're looking at the device owner, which may not actually be the hospital. So you have the device owner, you have the connection to the data center, you have the data center, the hospital itself, you have the connection from the hospital to the edge data center that owned by a different organization, the actual firewall intrusion detection system and similar things. So so you're talking about easily 6, 7, 8 different identities and setups that have to be integrated together. And when you start to look at these type of integrations, there's no way you're going to be able to control all that across all identities, and that's before you even take into consideration the heterogeneous decisions and what people decide to use in order to connect in. So this thing was designed in a way that if I have a system that's going to connect to your system, then what NSM allows us to do is that we declaratively state at the very top that these systems are allowed to communicate with each other. At the lower level, the details get negotiated. Like, should I use VXLAN? What parameters should we use? Maybe you want to use WireGuard for tunneling because you're going over an insecure network. So then, like, let's go and establish the what keys should I use? What IPs should I select in order to establish that connectivity? And so it allows us to establish a means to negotiate those connectivities while still giving each individual section, each company, the ability to control its own set of networks. And in the case of Kubernetes, for the reference implementation that we did, these actually are defined primarily through custom resources. So we have a CRD that describes that there's a workload that exists and that you can then connect to. So these are defined through the discovery is done through custom resources, which you can install using an operator. We have an NSM operator in the works that's being done with special thanks to Red Hat for helping us with that. And in order to install and to be able to drive these type of things and to be able to drive some of the identities through that operator as well. But then, what it does is it creates a split. Things that are high level, that are declarative, that you can then use in order to describe what that system should do, and then in the negotiation phase, we perform that negotiation, taking into account the context of the systems that's communicating with. These are things you cannot define up front easily without having to do a huge amount of work ahead of time, because you don't know what subnets you may conflict with when you're connecting with a group, or you don't know how the system may react over time. Or maybe you do know today, but then a month from now, you could have new CEDARs that get put in place, or new policy requirements that get put in place, and these systems react.
You can think about this. You remember the old adage when we started moving into the virtual world about pets and cattle, where it used to be that you'd have servers that were kept as pets, and you'd had sysadmins who would lovingly pet them and feed them every day, and they were all just a little bit different from each other. There was a lot of manual work, and so if you needed a new server, well, you started a couple quarters ahead looking for financing for it and finding the rack that you could put it in, and people would plan out the wiring, and oh, gee, do we have enough IPs on the subnet? And and then somebody would come in and say, well, gee, what version of this Linux distribution are we installing, and what extra packages do we need the sysadmin to install? And so getting a simple server was this enormously manual exercise. And as we've gone forward in time, we've simplified this and automated this and made more of this an immersion property until we come to the place that we are with pods and Kubernetes. Network service mesh is doing a very analogous thing to how you handle connectivity between domains, right? Because traditionally, if I had two domains that needed to talk, I would go and I would have my DMZ, and there would be meetings with you about your DMZ, and we would negotiate links, and there would be all kinds of things about policy. And then anytime anything had to move, you had 2 or 3 more quarters of tickets and company meetings and conversations, because all of the communication were pets at a level that was even absurd compared to what the servers were. And that's the piece that has to get solved if we're actually going to be able to move, because you've got a mismatch between the velocity of systems. We can now move really fast within a single cluster and really fast at the level of workloads. And it's brought us enormous benefits. But if the very, very fast thing suddenly hit the wall of multi-quarter, multi-ticket engagements, it becomes almost impossible to function at the larger scale. And that's what has to get fixed. You're muted, Dan.
Unmute. Hand waving.
There we go. Yeah.
So we're almost to the end of the hour, but so I wanted to sort of refocus a little bit to, you are a CNCF Sandbox project. You have a lot of big name, even OpenShift and other customers using NSM in different, it sounds like a lot of telco, a lot of edge scenarios, automotive, medical. What is the path, the next steps for your project in terms of CNCF? Are you still gathering steam to get incubated? Where are you looking for resources to help you out?
We're still gathering steam. We're still gathering steam towards getting incubated. And the other one is in good fashion, which is we're getting simpler. So because it turns out that as people want to do more stuff with network service mesh, the on-ramp has to be made simpler and simpler and easier as time goes on. So one of the exercises we're going through right now is we're in the process of doing a more modular refactor of how network service mesh works to make it even faster and easier for people to stand up more and more sophisticated network service endpoints to provide network services, because we have a breadth of people who are interested in doing various things, to make it easier to get network service mesh in and out of various environments. Basically there's a radical simplification going on in order to improve velocity of development across the entire ecosystem. And this also ends up, as it turns out, and simpler is a lovely thing, because as it's gotten simpler, we've also discovered we can make the system even more robust. So we already had in place a very good resiliency strategy around auto healing, but that resiliency strategy is becoming even more robust as we simplify the system. Because it turns out complexity has massive taxes everywhere.
Yeah, one of the things that we've done as well, and this slowed us down a little bit, but is proving to increase our velocity quite substantially now, is we went back and we had a monolith version of network service mesh, and we stepped back and said, okay, well, this monolith is actually starting to slow us down. It's starting to, every time we want to make a change, it's becoming more difficult to make a change to the core. And so what we did was we created an SDK, and then what we did was this SDK was designed for people to write their network services in, but then we made the realization that network service mesh itself should be written using that exact same SDK. So in other words, we should go through the same pain we're asking other people to go through in terms of, in order to build up these systems. And this has turned out to be immensely helpful, because it's helped enforce the modularity of the system. And so it allows us, like all the stuff we mentioned about identity is within a specific service. You can rip that service out, stick your own identity solution in. The same with policy. We're using Open Policy Agent as our reference, but if you have your own policy system you want to bring in, same thing. Same thing with observability, and the same thing with auto healing and so on. And so this allows us to scope down the specific thing that we want. And if we want to create a new version that has different properties to solve a specific problem where what we compose together doesn't quite fit your needs, you can compose together your own set of services that do fit your needs together. And so and each of those components is also we can also test in isolation. So we can set up, okay, we have a connection that looks like this coming in. What do you do? What are the results of that? And so we're very close to having a full release on this new version with this new SDK. And once we get that out there, then we're going to spend time helping others to stand up their initial versions of NSM in their labs, in their test environments, and so on, so they can get a feel of what it's like, and then we'll see where it goes from there.
Cool. So we are at the top of the hour. So I just want to remind everybody that on August 17th, the NSMCon is happening. And please click through that or scan it or however you want and check it out. There'll be lots of good talks there. As well as Frederick, you mentioned there's an NSM operator coming soon. So when that comes out, we'll do, hopefully another conversation and some demos and get some more information for everybody on how to deploy that. And again, There's lots going on at KubeCon the 17th, 18th, and 19th, but do spend some time with this group of folks, because I think this is an important piece of the puzzle. And then they've solved it. And if you want to get involved, definitely go to networkservicemesh.io and follow the links to the community, because there's some amazing people working on this project and some really interesting use cases too. So thanks again, Ed and Frederick, for your time. As always, Frederick, it's a pleasure. And Ed, welcome to the Commons. We'll get you back on. I can tell that the Fred and Ed show is a well-oiled machine here. I think there's lots of things we can talk about too. And I'd love to do this and have a demo of deploying it and
cool.
showing the visualization, maybe in the context of OpenShift as well, sometime when the new release comes out. So please come back. And with that, I'll let you guys go back to your day jobs, and I will go back to my vacation. And we will upload this along with the slides, hopefully in the next day or so. So look for that out on the Twitter's feeds, and we'll put it up on the YouTube station as well at RH OpenShift. So thanks, guys.
Thank you.
And come back soon, please.
Thank you very much.
Cool. Thank you.
All right.